electronegativity. The consequences of electronegativity are bond polarity. Actually, the major consequence of electronegativity is bond polarity. Ionization energy. Ionization energy, and usually this is the first ionization energy, is the energy required to remove an electron. And that's why last class we talked about the fact that ionization energy, the conversation is about making cations. Making cations, ionization energy. Electron affinity is the energy released. And this is why it's negative on the table. Released. When a neutral element picks up an electron. And last class, we looked at all the tables in the textbook. The best way to look at the periodic trends is to actually look at the numbers on the tables in the textbook. The last one is size. Radius, size. Atomic size or atomic radius. And the periodic trends go as follows. Three of them go up and to the right. Electronegativity, electron affinity, and ionization energy. The only one that goes in the opposite direction is radius. One thing that I want you to think about is the relationship between these two, ionization energy and electron affinity. These are not opposites. It sounds like it because you are making cations when you're talking about ionization energy. It's the energy required to remove an electron. And if you remove electrons, you're making cations. This one, you're making anions. And it sounds like you could think of them as being opposite, but they are not opposite. A reaction that symbolizes an ionization energy, a first ionization energy, would be for you to write sodium solid oxidation state L Zippo, coughing up an electron and becoming the +1 cation. That is an ionization energy. The energy removed, the energy required to remove an electron. Watch how this is not the opposite of ionization energy. So what happens in electron affinity? In electron affinity, it is a neutral element that picks up a proton. In other words, this is not you simply reversing this reaction. It's not where you give sodium +1 an electron. In electron affinity and all the periodic trends, they refer to the elements in the ground state. So this is actually, for electron affinity, it would be sodium 0 solid, where you actually force an electron for it to become sodium -1. That is electron affinity, is not the opposite of this one. Because the opposite of this one would just simply be, hey, let sodium +1 have its electron back. Not that at all. So, the likelihood of these reactions taking place are high when you're talking about elements on the left of the periodic table. So, of course, the ionization energies of the metals are going to be lower. They increase how? Up and to the right? Yeah, of course they do. Because these are the elements that would never want to lose electrons. These are the same elements that would love to get them. So the electron affinities are high in that area as well. We good? Okay. So which one would be a better example of an electron affinity? Which element should I use as a better example for electron affinity? Say anything in the upper right-hand corner. Exactly, good answer. Anything in the upper right-hand corner. So F2 oxidation state 0 in the gas phase, plus 2 electrons becoming 2 F minus 1. The likelihood of this particular item happening is high, because that's what fluorine wants to do. So the periodic trends reflect the reality of the elements on the periodic table and what they tend to do in their behavior. Kevin?
I would ask the question on this.
Which high-low? High-low. Which one has high, which one has low? And there's other types. We're going to get to this. We okay? There's one in particular that I want to do with you guys. So, are we understanding that ionization energy is making cations? Say yes.
Yes.
Ionization energy makes what? Cations. The electron affinity is about making what? Anions. Because you're shoving an electron, making an anion. Because this one, you're removing an electron, making a cation. Is that clear? Okay. So we talked about 2 exceptions, and we said we were going to talk about it today. There are 2 exceptions. I should probably not put 3 arrows. There are 2 exceptions to the ionization energy. Exceptions to first ionization energy. And to do that, to be able to understand it, what I want to do is now I want to write all of the electronic distributions of the elements across the entire period, starting with column 1. And what I want to do is I want to write all of the electronic distribution of every element up to fluorine. Every element up to fluorine. So here we go. What's the electronic distribution for everybody on this column? These are the so-called NS1s. NS1s. What are they? In the 1s orbital, there's only 1 electron. What's the electronic distribution for this guy? These are the NS2s. Okay. What are these guys? That's a P1, ain't it? What's this?
P2.
What's that?
P3.
What's that?
P4.
And what's that?
P5.
This is P3, P4, and now 1 and 2. P5? Yes. And then of course the full shell P6, correct? Okay. The trend for ionization energy. The trend for ionization energy is that it rises up and to the right. That means that it rises going to the right and up any column. Right. Because smaller elements will tend to pull electrons a little bit harder. So it's going to be a lot harder for you to rip out an electron from a smaller element than to rip it out from somebody on the bottom of the periodic table that has seven principal quantum numbers. And by the time you are looking at electrons in the outer fringe, who knows what's happening back there? The electrons are like gone, and it's like, I don't even know it was gone. And therefore, it's not that hard to rip out an electron, so the ionization energies are lower. Of course they are, for the guys down here. When the elements are small, they're looking at each one of their electrons, and the effective nuclear charge is a lot higher when they're closer to the nucleus. Fine. Let's talk about exceptions to ionization energies. The ionization energy is what? The energy required to take out an electron. Which electrons do you take out? The last ones. The last ones. And we might as well start the conversation right now. Lewis structures. Valence electrons. The last electrons, which is the next conversation we're having, Lewis structure. Which electrons are you actually dealing in? Which spaces are you actually dealing in? The last ones. The ones that are available for filling in or taking out electrons. Those are called valence. valence electrons. These are your S and P's. Valence is a word that's never applied to d orbitals, by the way. Never applied to d orbitals. It's always S's and P's. The energy of activation for all of the items in the first column would be the energy required to rip out that electron. The first ionization energy to rip out that electron. First ionization energy to rip out one of those electrons. First ionization energy, rip out that guy. First ionization energy, rip out that one. This one. Which one of these would you probably rip out? The doubled up one, probably. Because they're repelling each other, so it'd be a lot easier for one of those electrons to be lost. Because it's already sharing an orbit. I probably think you're right. And first ionization energy to take out one of those electrons. That's the amount of energy required to remove those electrons. And when you remove electrons, what are you making? Cations. Funny thing happens in the trend. And it goes like this. The numbers begin to increase, and all of a sudden, when it comes to the transition between 2 and 3, you notice that this one is unusually low. In fact, it's unexpectedly low. So that this number is a certain number. This one's higher because the trend goes up. And all of a sudden you come to this one and you go, oh, wait a second, this one's lower. That's not the trend. Okay, fine. And then it goes along, this one's higher. This one's higher. And then it comes to this one, and it happened again. Unexpectedly low. All the way down the column. So the exceptions occur in these two transitions. And going from this one to this one, and going from that one to that one. And that happens all the way down. If you looked at the tables on the in the textbook, you notice that. You know, another way of thinking that this one is unusually low because it dips in a trend that should increase. And it does increase. If you look at the trend from start to end, the numbers do go up. But in two spots, they dip. Another way of doing that, of reasoning this, is that this is unexpectedly high. Yeah, maybe that's the one that's unexpectedly high. Maybe this one is unusually high. Because both of those things are true. Now, why would that be? The answer is actually easier than you think. Look at this. This is a special condition. It is a full shell. So if you want to disturb a full shell, you're going to pay. Of course, it's going to appear that this one's unexpectedly low, but that's because this one's cost you too much. And it happens in two places. Roman numeral 2, all of them, all the way down the list. Roman numeral 2, nature protects a full shell. And the ionization energy for these items are actually switched with 3, the order, because this one is unexpectedly high. Why? Full shell. And it happened again. Nature protects. Nature protects special electronic distributions. And to have every single orbital in this p orbital with at least one electron occupying it is unusually symmetrical, unusually stable, and it doesn't have the extra one that's already bothering the other one. When is the other case in the trend where it's going to get really unusually high? This one. Because this is true perfection. These are the perfect gases. The ones that have the true complete shell. And ripping out an electron from those guys, good luck. Because then that one's way high. Do we understand why there are two exceptions in the trend? Ionization energies. Two exceptions in the trend. Yeah. Because nature protects unusual arrangements. This one being a full shell, and this one being a half-filled shell without repulsion. Coming to the next one, and nature says, yeah, you know what? There's nothing special about my arrangement. You can have that one. Take it. It's yours. I don't care. This one. Because there's nothing special about it. We good? So, in the ionization energy trends, the entire column, this one, is actually higher than that one. So pay attention to switch those when they ask you for the order. In the entire column, this one is going to be higher than expected. So make sure to switch it with the next one. We good? Any questions? Please look in your textbooks for the numbers so you can see them actually. The best way to do it is to actually look at the numbers in the textbook. Yeah, any questions left? Okay, there's a problem in study sheet number 6 that I want to do with you. And that is problem number 7. I want to do it right here so we can look at all of this. Did you have something? What was it? Yeah, tell me. Switch them. This one here is unusually high. So these two are switched all the way down. This one and this one are switched all the way down. Again, the best thing to do is to get that textbook and look at the numbers and go, oh yeah, the entire column switched. So that you know that all of them, across any period, any horizontal period, those two are switched. For reasons of electronic distributions. It says here, here's the type. A little while ago somebody asked, well, what kind of questions can you ask? These are all the types of questions that you can ask. Which are largest? Which is smallest? Which one makes a cation easier? Which one makes an anion easier? Let's analyze the questions. Which is the largest and which is the smallest? What periodic trend is that? Atomic radius. That's it. There's no other way of saying that. Which one makes a cation the easiest? Specifically, making a cation the easiest. What are they looking for? The item with what? Lowest. Absolutely. You don't need me at all. Ionization energy. The lowest ionization energy. How about making an anion the easiest? The highest electron affinity. The highest electron affinity. So don't check your common sense at the door. Read the questions and translate it into the periodic trends you already know. We good? Now, in question number 7, they have most energy and least energy. How about this one? Which one makes a cation the hardest? The one that has what? What does that translate into the trends? Which one makes a cation the hardest to form? The highest what? Ionization energy. The highest ionization energy. And your choices are ion plus 1, TL plus 1, TL plus 3, SB, NB plus 3, To answer questions on periodic trends, this is what I want you to do. And this is true of all questions of periodic trends. Since you are given a periodic table, I want you to grab the periodic table and put a dot in the box where they have those elements that are mentioned in the problem. So the first thing you do for trends is you grab your periodic table and you put a dot inside of those boxes. And these arrangements is indium and thallium, and what's Sp again? Antimony, and what's Bi? Bismuth. So what are we talking about? We are talking about In, skip 1, Sb, Tl, and skip 1, Bi. And so you would be having 4 dots on your periodic table, not a gazillion. This is just 4 elements. That's the first order of business. Organize the information and don't let something scare you. Fear is not part of this equation. This is the question about 4 elements. That's it. Let's answer the first one. Which is the largest one? What's that? Atomic radius. It increases what? Down and to the left. So what's that? TL. How many TLs do I have? 3. Hey, which one's bigger? The one that's in the ground state or the one that you ripped out electrons out of?
The ground state.
Of course. Next, which one's the smallest? How does the trend run? The trend runs down and to the left. So which one's the smallest? Up and to the right. What's that? This one? They want the smallest. How many SPs you got? The neutral, the one you ripped out 3, and the one you ripped out 5. Which one's the smallest? Done. Next, which one makes a cation the easiest? What's the trend? Making a cation the easiest. What's the trend? Ionization energy. Ionization energy. So making the cation the easiest, that means that it doesn't cost me much to make that cation. So it must be low ionization energy. So how does that trend run? Up and to the right. That trend runs up and to the right. So if I want to answer the question, who makes a cation the easiest, where am I looking? Bottom left. Is that right? So what do you got? Who's on bottom left? TL. Cation. So it means you're in the business of ripping out electrons. The easiest. What did we talk about in terms of energies of subsequent energies of ionization? The trend that you memorized is really called what? It's really called what? It's really called what? First ionization energies. Because electrons are coughed up one at a time. And each time, it costs you more to rip one out. So which one will make you a cation the easiest? The one that hasn't gotten any ripped out yet, or the one that has 1 and 3? So which one is it? The neutral one. Because it's going to be a lot harder for you to rip out an electron from something that's already positive. You're asking it to become even more positive. And it'll cost you. It's not impossible, but it'll cost you. So what's the answer to this one? TL. Which one makes a cation the hardest? What's that trend? Ionization energy. Because ionization energies are the ones that are the energies required to make cations by removing electrons. How does that trend run? Up and to the right. So if it's really hard to make an electron, what are we talking about? High ionization energy, where it's going to cost you to get rid of the electron. So where am I looking? Up and to the right. What do you got? Up and to the right in this trend. SB antimony. How many you got? You got 3 of them. And they want the hardest, the one that's going to cost me the most. SB plus 5. the easiest? What trend is that?
The
Or hardest?
electron affinity.
Or hardest? Say again?
Affinity, electron.
Electron affinity. How does that trend run? Up and to the right. So anion the easiest. What have you got here up and to the right? SB. So what are you looking at? These. Remember, these are not electron affinities are not the reverses of ionization energies. They are not. Electron affinities are with the neutral elements. So which one would make an anion the easiest? This one, an anion. Because if you start returning electrons to the plus 5s, that's not electron affinity. We talked about that. They're not opposites. We good? Okay. That's it for the periodic table.
What about the
Repeat the
hardest?
anion. What you said about anion?
If it's about making anions, what trend is it? Electron affinity. How does that trend run?
The top right.
Up and to the right. So if you want to make an anion the easiest, it's the thing with what?
With
The
no-
highest electron affinity, the one that wants the electrons the most. And who does that? I've got TL, I've got IN, SB, and DI. Who's that? SB.
Why do you use the neutral state instead of the plus one?
Because ionization energies are about making, electron affinities are about making anions. And you start with the neutral element. Making anions is not the opposite of making cations. It is not returning an electron to something that's already positive. Electron affinities start with neutral element. It's what the definition of electron affinity is.
And the hardest
That's
one
why I
would be-
made the point of writing the words not opposite.
And the hardest one would be TL.
Then the hardest one will be TL. Bottom left. We good? You guys okay? Tell me. The lowest electron affinity, bottom left. The trends run up and to the right. Lowest electron affinity. Guys, what else? Alright. About what I sent home. Are there any questions? About what I sent you home. Any questions? Everybody okay? Yeah, please tell me. 12 for 12, senior class. Study sheet number 12, senior class. Any questions on this one? On this, what I sent home? Any doubts? Anything at all? Yeah,
How much
tell
do
me.
you have to know about the people who
You have to know their major contributions in a multiple choice scenario. Their contributions in a multiple choice scenario.
So you see everything we wrote down?
What else?
Everything we wrote down?
Well, each one did one thing. They did all. They're all famous for one item. What else? Guys, what else? You guys are ready? That's it? You guys are, that's good? You guys are done? Okay. Alrighty then. Alright, let's talk about the shapes of orbitals. And if you think of anything, I can sort of leave
El
this
nombre de
here.
María Andrade quedó muy bonito. Los nombres están acá.
You draw a line on Friday.
That's the nivel.
That's it. This is more of the same. This, nothing I said today is new. We're just talking a little bit more about what we talked about on Friday. There's nothing new here. It is not. What I'm about to say is test 4. To me, mentally, water under the bridge. I'm all about test 4 now. It's all about test 4. Test 4 is in 3 weeks. Test 4 is in 3 weeks. Huh?
¿Por qué lo necesitan?
I'm all about test 4. And believe you me, sort of, so are you. Because in the studying for test 3, make sure you're reviewing for the final, and everything that we've talked about now gets a little bit of interconnection. You're now going to go into a part of the class where there's hardly any algebra. In fact, there is none. From this point on, algebra is over. And now we have more of chemistry. Yeah? I know, so that's good news for some people, but not for others. I know, because some people like the algebra part. I know. So, Let's talk about the shapes of orbitals, guys. And by the way, get that sheet memorized. Did you start memorizing it already? Make some time to get it memorized. What sheet am I getting you? You have it. The handout. The shapes of orbitals, folks. The shapes of orbitals. What is the shape of an s orbital? What's the shape of an s orbital? You guys go to orbitals.com? It's a sphere. What's the shape of a p orbital? Yeah, it's like a little infinity symbol. And how many of them are there? P orbitals. How many are there? 3. Yes, 3 orbitals. And they are called the px, the py, and the pz. And they run along the angles of the Cartesian coordinate system. And therefore, they lie at how many degrees from each other? And I won't tell your math teachers that you don't know what the angles are in the Cartesian coordinate system. If they are called the px, the py, and the pz, what are the angles between them? No, Papa.
It's 120 and 90.
They're called the px, the py, and the pz. What are the angles between them? 90, because there's one along the x-axis, there's one along the y-axis, and there's one coming at you. The px, the py, and the pz. That's what they're called. What are the shape of the d orbitals? And how many are there? What are the shapes? They're in the textbook. Take a look at it. 4 of them look like a little 4-leaf clover. And their names, you can try to recognize them, but their names depend on the plane that they're in. Like if it's a YZ one, then it exists on the YZ plane. That's what they mean. 4 of them look like this. Imagine if you took 4 balloons, 4 little balloons, and squished them in the center. That's what you would get in a 3-dimensional image. 4 balloons squished in the middle by their little tips, by where you blow on them. If you actually hold them 4 together, it's like a little 4-leaf clover, a 3-dimensional 4-leaf clover. And then there's one that's really funky looking. It looks like a p orbital with a donut through it. And I want to tell you that we didn't make that up. I know it looks like we did, but we didn't. The reason we know these are this way are mathematical calculations. These are plots. They are graphs. Absolutely graphs. There's no doubt. They are graphs, and they are the results. Every time, imagine you putting a linear equation in Excel and press the button, plot. What happens? What does your printer do? What's your printer do? Oh, that. With whatever slope. Correct? Okay. Think about that little exercise. If someone were to put in a computer something called a wave equation, the product of quantum mechanics, wave equations, 1932, a man by the name of Erwin Schrödinger had to invent a new branch of physics called quantum mechanics. Stuff so hard that you need 17 semesters of calculus to figure this out. Differential equations, 35, who knows? Imagine how crazy smart this individual was, that he realized that all of the descriptions of the atoms that they had up to that point required a brand spanking new branch of physics. 1932, the invention of quantum mechanics. Crazy stuff. And the basis of it goes like this. Can't really tell any given moment? You can't. Because items that are moving at the speed of light have a problem, and that is called an uncertainty. In other words, items that are moving at the speed of light have a certain uncertainty, and that uncertainty has a name. And the uncertainty is like this. If you're able to know where it is, you'll never be able to know the speed. And if you were able to clock the speed, it's already gone, so you don't know where it is. Imagine if you were driving to Orlando on the turnpike. And you can imagine this very easily because it's very close to a human experience. Regardless of your speed, a bystander, an observer on the side of the road with the correct equipment can clock you and obtain your speed in that snapshot in time where you passed in front of the measuring device. That same measurer, that same observer, can also say north on the Florida Turnpike, just north of Yeehaw Junction, mile marker so-and-so. The thing about atoms is that their electrons are moving at the speed of light, and there's no little tiny policeman to clock them and tell where anybody is. You can't. And because of that, this is Heisenberg. Uncertainty principle. So imagine my absolute pure joy when watching Breaking Bad for the first time. The main character, how many people watch Breaking Bad? If you didn't consider it homework, you need to watch it. Watch it immediately from the very beginning. Yes. Imagine my pure joy when the main character struggles to find a fake name, and out of his mouth comes Heisenberg. I fell out of my chair. This is the best ever. The best moment of television when this guy calls himself Heisenberg. It's called Heisenberg's uncertainty principle. That you cannot tell the position and the speed of an electron simultaneously because they're traveling at the speed of light. Not his fault. Not his fault. But that presents a problem because in quantum mechanics you can't really tell where anybody is. The best we can do, period. The best I can do is go with probabilities. Which is what the wave equations are. A prediction of the probability of finding an electron in a three-dimensional space. Exactly. Okay? And what they do is they input information about the probabilities of the three-dimensional space, and just like you with Excel, pressing the button that says print, so did they. And out comes the following. Here's my impression of what happened. When, just like you on Excel, they put wave equations into a machine and pressed print, the plot of the probability of finding an electron in a p orbital. Probability of finding an electron. Ready? The first iteration tells me there's a probability of finding an electron there. The second iteration, there. Okay? It's a probability. There's a probability that this electron might be on the moon. It's a probability. High, low, eh. And then they realize, hey, crank them out faster. This is going to take forever. Crank them out. And here's what happens. And it doesn't take a genius to take a step back and go, I don't know, what does that look like to you? I don't know. Yeah, P three-dimensional space. Okay? They're not made up in any way, shape, or form. So, you gotta know what the shapes are. You gotta know what the shapes are. You gotta recognize the orbital by its shape. So when you see something like this, you go, hey, that's a d orbital. When you see something like this, you go, hey, that's that funky d orbital. And when you see something like this, you go, hey, those are the px, the py's, and the pz's. And just one more time, what are the angles between them?
90.
90 degrees, because they're called the px, the py, and the pz. What are the angles between them? 90. All right. Lewis structures. Your favorite Lewis structures. Your favorite. Now I gotta ask you a question. How did you learn? What are the different ways that you learned to do Lewis structures? How many people learn to do them with dots? Like, say for example, if I have to draw methane. How many people did this? I just want to know. Just raise your hand side. Okay, put your hands down. How many people did quick accounting of the electrons and just drew the line? And did some kind of math of available minus used equals excess and distributed leftover electrons. Let me hear it. Let me see it. Okay, that's fine. That's fine. All right, so now I know I'm going to do it mostly this way. And then I'm going to let you guys choose. I'm going to do it two different ways, but I'll start this way, where most people remember. And then I'm going to show you two different ways. There's like 4 different ways of doing it. You pick one and go with it. There's like 4 different ways, and I'm going to show you 2. So pick one and go with it. Lewis structures. Lewis structures. All right. Let's do the Lewis structures of water, of PCl5, Lewis structure of ammonia, Lewis structure of NH4 plus, Lewis structure of C2H2. Alright, I'm assuming you've had this before. So this is not the way I would do this if I thought you had never seen this before. So I'm taking advantage of the fact that you have had this before. So Lewis structures, the central element is the one listed first, the one with the lowest subscript, never hydrogen. So when I'm drawing the central element of water, what do I write at the center?
Oxygen.
Never hydrogen. Never hydrogen. The one listed first, or the one with the lowest subscript, never hydrogen. So which one do I put at the center?
Oxygen.
Oxygen. And hydrogens are always in the periphery. Poor things. They can never throw an electron party themselves. They're just, they're always invited, but sometimes they don't even have their own electrons, sadly. So how many electrons do I put in for the hydrogen, and how do I know? What are the valence electrons, and how do I know? The periodic table, those are your groups. 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, and full shell. Not interested in bonding really, but if you make me, I'll do it. I must. How many electrons does oxygen have in its valence shell? 6. 6. I know when you said 2, you meant 6. I know. For very large numbers of 2, it should be 6. How do I place the dots? How do I place the dots around an element? In other words, can I write, when I do phosphorus, how many dots is phosphorus going to get? 5. So can I just go ahead and do them like this, like nice and a little round, in a little circle?
No.
Can I do that?
No.
No, I'm not allowed to do that. Actually, there's a rule, and the rule says that I have to do them in pairs, pretending that there's a square box around the element. So if I have to put more than one, I put one at a time on each side, and then I double them up. So I don't put that 5th one here. I have to put it along with one of the other ones, and it doesn't matter which side. But that's the rule. You good? So what's the center element here? Nitrogen. And 1, 2, 3, 4, 5. What's the center element here?
Nitrogen.
1, 2, 3, 4, 5. What's the center element here?
Carbon.
How many? The 2 carbons. Yeah, you have to. And how many valence electrons do they have? 1, 2, 3, 4. 1, 2, 3, 4. And distribute the hydrogens. Distribute the hydrogens. 1 on each side. Sure. How many electrons does hydrogen have? Hydrogen always brings his one and only. Gets invited, he brings his one and only to the party. That's what he does. So now, hydrogen with his one and only. Hydrogen with his one and only. How do I make this? How to make the structure? And that is the essence of a covalent bond. That is the essence of a covalent bond. In other words, I have 1 electron, he has 1 electron, and we share it in a covalent bond. Depending on the difference in electronegativities, we pull in either direction. If we both have the same strength, nobody is a winner of the tug of war, and the electrons are evenly distributed between us. So every time you write a stick, remember what you're writing is a pair of electrons that are shared. Is a pair of electrons that are shared. So how about this one? PCl5. 1, 2, 3, 4, 5. They made me put 5. It says PCl5. How many electrons are in chlorine? 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Am I paying attention? Do you think I'm paying attention? 5, 6, and 7. To where I'm writing the dots? Say no.
No.
1, 2, 3, 4, 5, 6, and 7, because it doesn't matter. Because it doesn't matter. 1, 2, 3, 4, 5, 6, and 7. Because it doesn't matter. The way that I'm going to draw the Lewis structures here in class is as if you were drawing them. I know what they look like, and if I put the dots ahead of time where I know they go, you're screwed. Because when you go home, you'll never know where to put the dots. So I'm doing it the way you'll be doing it. And I'm telling you that the dots don't matter. Because when it comes time to connect the dots, I'm forced to make pairs of electrons being shared between atoms. And I have no choice but to pair that guy with this one, that guy with that guy, this one with this one. And they made me do it. It says draw the Lewis structure of PCl5. They made me do this. And yes, I can clean it up. Of course I can. So when I clean it up, and that's a Lewis structure of PCl5. And the same goes for all the others. How about this last one? How about this last one? Connect the dot, connect the dot. And now what? 1, 2, 3, a triple bond. Do I clean it up? Absolutely. Triple bond, hydrogen, and hydrogen. We good? Any questions? All right, so on Wednesday we continue with Lewis structures, and we're going to get into the shape of molecules.